Okay, so this warm-up question, what would we do with this? First of all, we've got to determine the relationship. So we have two angles. Are they equal? Are they supposed to be equal to each other? No. So the other possibilities, do they add up to something? Yes, and we know they have to add to 180. Good. So 3x plus 9x has to add up to 180. What do we do from there? You got it. 3x and 9x make 12x. And then divide by 12. So x equals 15. All done? No, what do we still need to do? Fine. Perfect. Replace the x with 15 and then we multiply in each. So 3 times 15 is 45 degrees. This will be 9 times 15 is 135. Any questions? Let's try this one since we're on a roll. See what you come up with in this one. So this one's just a little bit more involved. What's the relationship between the two angles this time? They're equal. Good. So 3x plus 17 has to equal 5x minus 29. And it doesn't matter which one you put on each side. You could switch them around if you wanted to too and have the 5x minus 29 first if you prefer. Doesn't really matter. But now that we have the equation set up, we notice that there's an x on each side. So what do we have to do? Perfect. We're going to subtract 3x to get rid of it over here, leaving us with just a 17 here. We'll subtract 3x over here to get 2x minus 29. Now, we got to solve for x by add 29. 46 equals 2x, and divide by 2. So 23 equals x. All done? No, what do we got to do? Put it back in here. So 3 times 23 plus 17. 3 times 23 is 69, plus 17 is 86 degrees. Try over here. 5 times 23 minus 29. 5 times 23 is 115 minus 29 is 86. So we get the same answer on both sides. Obviously that drawing is not done to scale. Any questions on either one of those? Okay, cool. Any questions from the homework from on Tuesday at all? You may have noticed that I did problems in class that were maybe a little bit more, the homework was a little bit easier than the examples I did in class at least. For the perimeter problems, I got a little bit more involved than what the homework did, just to kind of give you a little bit of a push. We are going to come back in a few weeks to problems that are more difficult, like some of the examples I did, just a heads up on that. Anyway, our next step, we've got a few different things we want to cover tonight. We're going to start out just kind of reviewing some of our rules for powers here. We know, of course, that this means eight to the third power, or 8 times 8 times 8. 3 eighths multiplied together. And we can multiply that to get 512. X to the third power, of course, then means 3 x's multiplied together. And if you might recall, if we had x to the third power times x to the fifth power, we get x to the eighth, because x to the third is 3 x's multiplied together. X to the fifth is 5 x's multiplied together. If we multiply those together, we now have 8 total x's being multiplied together, or x to the eighth. So even though it looks like we're adding, we are still multiplying. It's just the powers the exponents add up. So if I have y to the 17th times y to the 5th, I'm going to get y to the 22nd. Good. 17 plus 5 is 22. If I have z to the 3rd times x to the 9th, I'm going to get trick question. Different names. I can't combine the powers. I'm still multiplying them. I still multiply x to the 9th, z to the 3rd is multiplied. That's a result. But I can't combine the powers if they have different bases. I can only do this if the base, which is this part, is the same on both of them. So what if I add a number into that? Like 7x to the 3rd times 13, x to the 8th. Well, just like any other time, we're combining the counts. What's 7 times 13? 91. And then I combine the names. X to the 3rd times x to the 8th is x to the 11th. 3 plus 8 is 11. So I have 15 y to the 9th times a negative 3 y to the 5th. 15 times negative 3 is negative 45. Y to the 9th times y to the 5th. Y to the 14th. What if we have two names? So here we have 6x to the 3rd y to the 5th times 9x squared y to the 4th. Well, I still combine the counts. 6 times 9 is 54. And then I can combine each name separately. X to the 3rd times x to the 2nd is x to the 5th. Y to the 5th times y to the 4th, y to the 9th. Perfect. So if I have a negative 15, x 7th, y z to the 3rd, times 4, x to the 5th, y to the 5th, z to the 4th. What do I get? I'll have you guys try that one quick on your paper. So we have, let's get this out of here. Negative 15 times 4 makes negative 60. Perfect, negative 60. No, negative times a positive is negative. So x to the 7th times x to the 5th is 12. Good, 7 plus 5 is 12. Y times y to the 5th. Y to the 6th. Good. We think of that as y to the 1. And z to the 3rd times z to the 4th. Z to the 7th. Very good. Well, let's look at something a little special here. At least you're faking the right attitude. So on this one, we got 3 of them in here. What are we going to do? Well, we've got the counts. 8 times 4 is 32. Notice, just like we did with any of our other order of operations, we're doing 2 at a time and we're going left to right. A squared times a to the 5th, a to the 7th. Now the b, there's no b over here, so what happens to it? It just stays b, nothing changes. Then we have the c squared. Does it matter what order we put these in? Could this have been a to the 7th c squared and then b? It could have been any order and it would have been mathematically correct. But yes, proper grammar says alphabetical order. Kind of like grammar in your writing, there is grammar in math. It's not wrong if you don't put them in order, but it's more proper to put them in order. So now that we have that done, we can bring down the 5, a to the 7th, b to the 3rd, and work with that. 32 times 5, 160. A to the 7th times a to the 7th. 7 plus 7 is 14. Good. B times b to the 3rd, b to the 4th. And c squared has nothing to combine with. So it's 160, a to the 14th, b to the 4th, c squared. What's that? Uh-oh. What'd you miss? Or did you see what you did? Okay. We've also worked a little bit with things like this. Now this here, remember we said we could just do a long multiplication, but our shortcut was to distribute. We always check, is there anything we can do inside those parentheses? Well, 5x to the 3rd minus 5x squared, do they have the same name? No. X to the 3rd is slightly different than x squared. So it's not quite the same name. I cannot combine those. So is there anything I can do to the parentheses? Yeah, it's times 8x. I can multiply anything. So 8x times 5x to the 3rd, 8 times 5 is 40. X times x to the 3rd, x to the 4th. Now x times negative 2x squared, 8x, sorry, times negative 2x squared. 8 times negative 2, negative 16. X to the 3rd. Very good. X cubed works too. Do this one quick. Let's see how you do. So again, there's nothing to do inside the parentheses. But what we can do to the parentheses is multiply by a negative 7x to the 5th. So negative 7x to the 5th times 3x to the 8th. Negative 7 times 3 is negative 21. X to the 5th times x to the 8th, x to the 13th. Perfect. Negative 7x to the 5th times negative 9x to the 4th. Positive 63. Very good. A negative times a negative is a positive. Bless you. X to the 5th times x to the 4th, x to the 9th. Perfect. Anybody have any questions on how we got to that? Okay. Well, then we could get something just slightly more complex. Something like this. Just a little bit more complex, right? This is just an order of operations problem. There's subtraction and there's multiplication. You might be saying, well, what about this? Is that addition? Not really, because can I combine those two numbers? No, that's actually just a two-digit number is all it is. So I'm taking that times the 5, actually not times 5y to the 3rd, it's times negative 5y to the 3rd. So the 9y to the 7th up here doesn't change. Negative 5y to the 3rd times 4y to the 6th is, so negative 5 times 4 is negative 20. y to the third times y to the sixth, y to the ninth. Y to the ninth, good. Now negative 5y to the third times 2y to the fourth. Negative 5 times 2 is negative 10. Y to the third and y to the fourth is y to the seventh. Then we still have the minus y to the seventh. So now here we've got things we can combine. We've got 9y to the seventh and negative y to the... Oops. I rolled that out wrong, but that's okay. It'll work. Anyway, so we've got the 9y to the seventh. I can't combine that with the negative 20y to the ninth. There's nothing here that I can combine with the negative 20y to the ninth. So I'm just going to write that out. But I do have 9y to the seventh, negative 10, and negative 11y to the seventh. 9 and negative 10 make negative 1y to the seventh. Negative 1 and negative 11 make negative 12y to the seventh. Does that make sense? Good. 9 minus 10 made negative 1. Negative 1 and negative 11 makes the negative 12.
So can't we still combine those two then?
Y to the ninth and y to the seventh are different names.
Oh.
So you've got to have exactly the same power to combine them. And that is a common mistake I will see made on a test as people try to combine that, like a negative 32y to the 16th or something like that. Can't do it. When you add or subtract, you must have exactly the same name. So let's look at 4x to the fifth times 2x to the third minus 5x minus 3x to the third times 7x to the fifth minus 2x to the third. What are we going to do here? Work left to right. So you got the first parentheses here. Is there anything I can do in there? No. To the parentheses? Yeah. Once again, I'm multiplying by a 4x to the fifth. Or 4x to the fifth times 2x to the third is 8x to the eighth. Good. 4 times 2 is 8. X to the fifth times x to the third is x to the eighth. 4x to the fifth times the negative 5x. Negative 20x to the sixth. Good. Over here now, nothing to do in those parentheses again. Get rid of that dot so it doesn't look like a division there. Nothing I can do inside those parentheses. I cannot subtract those because they have different names. But I can multiply by negative 3x to the third. Negative 3x to the third times 7x to the fifth. Negative 3 times 7 is negative 21. X to the third and x to the fifth is x to the eighth. Negative x to the third times negative 3x to the third times negative 2x to the third is positive 6x to the sixth. Perfect. Now what can we combine? Perfect. 8x to the eighth and negative 20x to the eighth makes a negative 13x to the eighth. Positive 8, negative 21 is a negative 13. Negative 20x to the sixth and positive 6. Negative 20, positive 6 leaves us at negative 14x to the sixth. What do you think? Good stuff? Okay. Well, a little bit of a review from last class. If I asked you to find the perimeter of this rectangle, what would I do? Well, I could do 7 plus 12 plus 7 plus 12 if I really wanted to, couldn't I? Just add up the sides, which will give us 38. But we had a formula that made that a little shorter for us. The perimeter is equal to 2 times the length plus 2 times the width. So we could have just done 2 times, what's the length? 12 plus 2 times 7 is the width. And now 2 times 12 is 24. 2 times 7 is 14. We add those to get 38. Perimeter is 38. Well, what if we had the sides listed like this? Our perimeter is equal to 2 times the length, so it's going to be 2 times 20x to the 4th, plus 2 times the width, so 2 times 7x to the 4th. Now we have to combine. 2 times 20x to the 4th is 40x to the 4th. 2 times 7x to the 4th. Positive 14x to the 4th. And then combine them. 40 plus 14 is 54. X to the 4th. Notice the powers stay the same. Again, I can combine those because they have x to the 4th and x to the 4th. They're exactly same variable and power. What if I ask you to find the perimeter of this? Well, 2 times the length is going to be 2 times 3x to the 5th plus 2x to the 3rd. Plus 2 times the width is going to be 2 times 5x to the 3rd minus 2x. What do we do next? Multiply by the 2. 2 times 3x to the 5th. 6x to the 5th. 2 times 3x to the or 2 times 2x to the 3rd. Positive 4x to the 3rd. 2, this is a positive 2, so it's 2 times 5x to the 3rd. Positive 10x to the 3rd. 2 times 5 is 10. And then 2 times a negative 2x. Negative 4x. All done? Not yet. The 5x to the 5th, or 6x to the 5th is okay yet. But we have 4x to the 3rd and 10x to the 3rd, which makes 14x to the 3rd. And minus 4x. Questions? Find the perimeter of that. Find an expression for the perimeter of that. So, the perimeter is going to be 2 times 7x to the 4th plus 3x plus 2 times 5x to the 4th minus 2x. So we're going to multiply by 2. 2 times 7x to the 4th is 14x to the 4th. 2 times 3x, 6x. This is a positive 2, so it's just 2 times 5x to the 4th. Positive 10x to the 4th. And 2 times negative 2x. Negative 4x. And then 14 and 10x to the 4th make 4x to the 4th. 6x, negative 4x. 2x. There we go. Questions? What if we're talking about area? And I want to find an expression for the area of these two. And the area is the length times the width. So I'm going to have, and I'm going to switch it around. I'm going to put the width first, actually. The 7x to the third times 3x to the fifth minus 2x. And all I have to do now is multiply. 7x to the third times 3x to the fifth is 21x to the eighth. 7 times 3 is 21. X to the third times x to the fifth is x to the eighth. 7x to the third times a negative 2x. Perfect. Negative 14x to the fourth. 7 times negative 2 is negative 14. X to the third times x. We consider that x to the 1. 3 plus 1 makes 4, so x to the fourth. Find the area. I'll give you a minute to work on that one. So, we'll go 5x squared times 19x minus 5. What do we get? Okay, good. 5x squared times 19x is 95. X to the third. And 5x squared times negative 5 is a negative 25x squared. Questions? Okay. Well, our next step, we're going to switch gears just a little bit, and we're going to talk about factors. Factors are numbers that divide into another number. So the first thing we have to figure out is defining what it means to divide into. And I'm just going to define it by example. 24 divides by 6 because 24 divided by 6 is 4. There's no decimal, no fraction, no remainder. Divides evenly with no fraction, remainder, or decimal. So if I were looking at 24 and I wanted to find the factors, well, 1 doesn't count. Well, it evenly goes into it without any remainders. 1 doesn't count because any number can be divided by 1. Can 24 be divided by 2? Yes. 3? Yes. 4? 5? 6? 6? Yes. 7? No. 8 is a yes. 9? 10? 11? 12? 12 is a yes. Now at this point, I'm going to stop. Why am I going to stop? Well, because 12 is half of 24. 24 divided by 2 is 12. Anything bigger than that, if I divide 24 by it, I'm going to get something smaller than 2, and, well, it's either going to be 1, which doesn't count, or a decimal. Technically, 24, in some case, depending on the book and how you're defining factors, some book defines 24 as a factor because you can divide itself. But for all practical purposes, it doesn't behave as a factor. A factor should be smaller than the number it divides. So the 24 and 1 doesn't count. So there's a complete list of factors for the number 24. Well, looking at that, it would be nice to be able to look at a number and quickly tell whether it's divisible by another number. 24 was easy because we've worked with 24 a lot. But what if we had something like 171? Trying to list factors for that is not so easy. So let's take a look. We'll come back to that. But let's talk about divisibility rules. How can I tell if something is divisible by 2? It's an even number. And by even number, that means it ends in 0, 2, 4, 6, or 8. Anybody tell me how to tell something divisible by 3? Anybody remember? No. Nice try, but no. 6 is divisible by 3, and it's not. Sum of the digits. What on earth does that mean? $258. Is that divisible by 3? Well, what's 2 plus 5? 7 plus 8 is 15. Is 15 divisible by 3? Yes. So 258 is also divisible by 3. The sum of the digits is divisible by 3. The number is divisible by 3. Now this comes in really handy when you get something like this. Okay, let's see where I'm sitting here. Like that. If we want to figure out if that's divisible by 3, what's 7 plus 8? 15 plus 7, 22 plus 6, 28 plus 5, 23 plus 3, 36. Now, if I'm not sure if 36 is divisible by 3, what's 3 plus 6? 9. 9 is divisible by 3, so 36 is divisible by 3. So 787,653 must be divisible by 3. Kind of cool. 4. Now, for what we're doing, realistically, we just divided by 2 a couple of times. We've divided by 4. But there is a way to tell if something's divisible by 4. It's not really useful. Well, it's a little more difficult. But we look at the last 2 digits. And let me show you an example of that. And this number, 798,392, all we care about to tell if it's divisible by 4 is the last 2 digits. Is 92 divisible by 4? It is. So this whole number is divisible by 4. Now this is not terribly useful because how many of you have memorized your 4s from 0 to 100? I didn't think so. So I mean, it's not terribly practical. But I can look at this very quickly and tell it's divisible by 2. If I were to divide it by 2, I'd see it could be divided by 2 again, and I'd do that. How do I tell if something's divisible by 5? Ends in 0 or 5, or 5 or 0. So again, none of the other digits matter. 7,832,695. Is that divisible by 5? You bet. Ends in 5. So it's divisible by 5. 6. How to tell if something's divisible by 6? Oh, it's divisible by both 3 and 2. It's divisible by 6. Is that divisible by 6? How many of you just started adding up digits? A few? I can tell you it's not divisible by 6 really quickly. Anybody tell me why? It's not, yeah, it's not even. It's got to be divisible by 2, so it's not even. That's really easy to check, so I usually check that first. That's not divisible by 6 because it's an odd number. It can't be divided by 2. Oh, what do I have there? This getting old thing really sucks. I used to be able to rattle these examples off without even thinking about it. Now this one, first of all, is it divisible by 2? Yes. So now I'll check to see if it's divisible by 3. 4 plus 3 is 7, plus 7 is 14, plus 6, 20, plus 3, 23, plus 4, 27. If I don't know, 2 plus 7 is 9. 9 is divisible by 3, so 27 is. This is divisible by 3, so it's divisible by both 3 and 2. It's divisible by 6. How can I tell if something's divisible by 7? Can anybody tell me? Yeah.
So, what's the answer to 6 then?
Yeah, this is divisible by 6. Yes, it is divisible by 6. So how do we tell if something's divisible by 7? Anybody know? Calculator? Yeah. I actually do not know of a rule for dividing by 7. If any of you find a rule that allows you to decide quickly if something's divisible by 7, write it up and let me know it. If it works, I'll give you extra credit. In fact, I'll give you an A in the course. And I'll publish it, get rich, retire. Yeah. They've been looking for a rule for hundreds of years for 7. They haven't found one yet. And I'm serious. If you find one, I will give you an A in the course so I can retire. You can spend years getting it. Yeah, I would not recommend going home and spending a lot of time over the weekend looking for it. It really wouldn't be productive. Okay, so tell if something's divisible by 8. Again, this is one of those that's just like the 4 is not terribly useful. You look at the last 3 digits. So if you had 759,136, to tell if that's divisible by 8, we look at the last 3 digits. Is 136 divisible by 8?
Yes.
It is, yes. So this whole number is divisible by 8. Now the question is, how many of you have your 8s memorized from 0 to 1,000? Okay, yeah. The rule for 8 is not terribly useful again. But just like with 4s, to divide by 8, if I divide by 2 once and then a second time, I can divide by 2 a third time, I'll have divided out the 8s. So I don't really need a rule for 8. I can just keep dividing by 2. How about 9? Well, I could just divide by 3 a couple times and I've taken care of the 9. But 9 does have a rule, just like 3 is the sum of the digits. Only now the sum of the digits has to be divisible by 9. What do I have here? So on this one, add up my digits. 7 plus 5. 12 plus 3 plus 2 plus 1. 18 plus another one. 19. Is that divisible by 9?
Yes.
19 is not divisible by 9. No.
I was still on 18.
But if I had this number, that's okay. I thought it did 18 when I was making it up myself. So 7 plus 4 is 11. Yeah, plus 3 is 14, plus 2 is 16, plus 1 is 17, plus 1 is 18. 18 is divisible by 9, so 743,211 is divisible by 9. How about 10? 10 is an easy one.
That's what ends with 0.
Ends in 0. So does that divide by 10? Yes, it does. It ends in 0. You like that one? That one's pretty simple. Now, want to define rules like, or 2 terms here. The reason I'm going to define these terms is as we look at divisibility rules, there's an important step here. Talk about something called prime numbers. Prime numbers have no factors unless you consider 1 in themselves. So like a prime number would be like 7 is a prime number. There's no number that divides into 7. 17 is a prime number. So don't get hung up on the 7s because 27 isn't prime. How about 13? Is that prime? Yes. How about 23? There's nothing that divides 23. How about 57? 57 is what we call a composite number. Composite numbers have factors. They can be split up into smaller components. That's composite. 57 can be 3 times 19. So composite numbers have factors other than 1 in themselves. The reason I bring that up, because when we were doing these divisibility rules, we talked about 4, that we didn't really need a divisibility rule for 4 because we just keep dividing by 2. Because 4 is a composite number. It's made up of 2 times 2. 6, same way. We didn't really need a rule for 6 because it's composite numbers. 2 times 3. So we can just divide by 2 and then by 3. Same for 8 and for 9. 8 was 2 times 2 times 2. We just divide by 2 3 times. 9, we divide by 3 twice. So for 12, do I need a divisibility rule? No, I just divide by 3 and then 2 and then 2. 12 can be written as, I should probably write it better form. 2 times 2 times 3. That would compose 12 if I multiplied those together. So divisibility rules from here on out, we don't need one for 12 or 14 or 15 because they're made up of smaller numbers that we can just divide by the smaller numbers. But 11 is prime. 13 is prime. 17 is prime. 19. So they do have divisibility rules for many of those. The problem is once we get past 10, the rules get to be incredibly complex. For example, let's look at the divisibility rule for 11. Oh, what are the others? So let's look at that one. 729,366. The divisibility rule for 11 says you start with the first digit and you take every other digit after that. So 7, 9, and 6. 7 plus 9 is 16 plus 6 is 22. Then you go back and you take the digits that are left. 2, 3, and 6. 2 plus 3 is 5 plus 6 is 11. Now you take those numbers and you subtract them. Doesn't matter which one's bigger or smaller. You take the bigger one minus the smaller one. If you get a number that's divisible by 11 or 0, if you get 0, that's divisible by 11. So this number is divisible by 11.
66,306 times.
Yep. This one's divisible by 11 because 8 and 4 make 12. 4 and 8 make 12. The difference is 0. So that's divisible by 11. Kind of weird, huh? Okay. Like I said, that rule is complicated enough that to me, especially since we have calculators, it's easier just to divide by 11 than it is to use the rule. The only ones I use when I'm looking at dividing numbers, I first will look to see if it's divisible by 10. Why? Well, because it'll end in a 0. It's really quick to find. If it's not divisible by 10, I'll look for 5. Because I have to look to see if it ends in a 5. Why don't I look to see if it ends in a 0? What if I wanted to end in 10, right? Then I drop down to 2 because 2 is pretty easy. I look at that last digit to see if it's even. And then I'll try my 3s because the 3s take a little bit more work sometimes. And then after that, hopefully it's divided by something and I can move on with life. It is a little bit past our break time, so let's get our break in here. It's 4:22. We'll come back at 4:32 for our second.